So this module 4.1 is asking you to look at a molecule in 3 dimensions, and it's really getting after 3 different things. It's getting after geometry, hybridization of a molecule, and polarity. And so what we're using to look at these different things is we're looking at, well, what does a specific atom have with respect to any sort of bonds or anything like that. And so we're going to get into that first with our geometry. Okay, so as a couple, well, the first thing that you need to be able to do with this, you need to be able to draw a Lewis structure. And so when we talk about geometry, if we talk about a molecule like CO2, what we're asking the question is what does this molecule look like in 3 dimensions? And when you draw a molecule like CO2, what you'll find is that it has 2 lone pairs of 2 oxygens on each side of it that are connected through double bonds. Each of these oxygens has lone pairs of electrons. Now, what's important to know about this is that these oxygens, they are as far away from one another as they can possibly be. Now, these spaces, the double bonds, they are as far away from one another as they can possibly be. So these are a total of 180 degrees away from one another. Now, if we take a molecule like BF3, and this is a molecule that would be considered linear. If you take a molecule like BF3, at the center you've got boron, and then you've got 3 fluorides, and I'm not going to draw the electrons on my fluorides, but this is what that molecule looks like. Okay, boron is a unique example of a molecule that can, of an atom that can exceed the break the octet rule by not having a total of 8 electrons around it. And so what these bond angles end up being is approximately 120 degrees. So these molecules, these fluorine atoms and these single bonds, they want to be as far away from one another as they possibly can be. And it just so happens that they end up on the same plane, and these are trigonal, or this is a geometry that is known as trigonal planar. Now, if we take 2 different molecules, NH3 versus CH4. Okay, now let's look at these 2 different compounds. NH3 looks like this. Oh, rats. I'm sorry. Got in the process of drawing it. NH3 looks like this. So it has a lone pair of electrons right here, and then it's got 3 bonded hydrogens. CH4, on the other hand, has 1, 2, 3, 4 hydrogens. Okay, now I'm going to talk about the CH4 molecule first. CH4, these individual bonded hydrogens are as far away from one another as they can possibly be. And in these examples, they take up the space of 3 dimensions, the X, Y, and Z plane. Now these degrees, or these angle measurements, are approximately 109.5. Now, if you think about that, you'd think, okay, that's almost 110 degrees. We've got 4 bonds. So if we added those up, that would be about 440 degrees. Well, you're right, that is the addition, but you have to consider a rotation about a circle, that is 360 degrees. So obviously, it can't be 440. Well, the reason for that is this bond angle measurement, 109.5 degrees, is taking into consideration not just the X and Y plane, so there would be our Y and our X plane, but it's also taking into consideration the Z plane. So we're looking at this in 3 dimensions. Okay, so if you compare that, this is a molecule that would be considered tetrahedral. It has 4 atoms that are surrounding a central atom, and they are all equidistant from one another. Now, if we take something like NH3, what NH3 has that makes it unique is that it has a lone pair of electrons. And so that lone pair of electrons, well, it's going to occupy a lot more space than these single bonded hydrogens. And what this ends up looking like is hydrogen, hydrogen, and here's our lone pair of electrons. This lone pair of electrons is pushing down on these hydrogen bonds, these nitrogen-hydrogen bonds. And so it's almost like there's a small pyramid, and then there's this additional pair of electrons. And this is an example. is a molecule that the geometry is known as trigonal pyramidal. So you have this little pyramid made up of basically 3 different components, and this lone pair of electrons is going to be depressing those. And so these bond angles are less than 109.5 due to the fact that this lone pair of electrons is kind of forcing them to be smaller than 109.5. Now, hybridization is something that we kind of have to look at with respect to, or in a similar way as geometry, but the way that this shakes down is we're using what's known as the valence bond theory. And this valence bond theory is basically based upon the idea that your valence electrons are establishing bonds between atoms. So if we take something like CH4, well, it's the valence bonds of carbon that are making those bonds take place. And so if we think about the valence bonds of carbon, we've got 2s2, 2p2. So what that means is we've got a pair of, or we've got s electrons and p electrons that are establishing those bonds. Now, if you think about it from the other vantage point of hydrogen, well, hydrogen's only bringing in s electrons. And so what we need to do is we need to utilize the placement of the electrons, or valence electrons in carbon, and get those to match up with our s electrons from hydrogen. And the way that we do that is if we look at an orbital diagram of something like carbon, we've got a valence that looks like this. What we need to do is we need to take these 4 orbitals and combine them with one another. And by doing that, we will make what is known as a hybrid orbital that is made up of, or a series of hybrid orbitals that are made up of 1 s orbital and 3 p orbitals. And it will look a little bit like this. And this orbital, since it is made up of 1 part s and 3 p's, this is known as an sp3 hybrid orbital. Okay, so what this gives us, though, that's important, is we have 3 spots where a single s electron from 1 hydrogen can drop in. Then another s electron from a hydrogen can drop in and drop in and drop in. And so by doing this, we are merging, we're merging orbitals, and we're making something that another atom can kind of get involved with. Because if we have an sp3 hybrid orbital that is basically 25% s and 75% p, okay? But it has s character, so that electron in the s orbital of hydrogen is able to share, or be shared. Okay, now when it comes to identifying the hybridization of a specific atom, one of the ways that you can do it is, well, you have to look at what is surrounding that specific central atom. So if we took something like CO2, we drew CO2 a moment ago, and it's got our double bonded oxygens. What is the hybridization of carbon? The way that you do this, or kind of a shortcut to do this, is you look at, well, how many things are surrounding that central carbon? Well, there are 1, 2. We've got 2 oxygens surrounding our central carbon. And so what we're going to need is we're going to need 1 s orbital and 1 p orbital. And that's going to make an sp hybrid orbital. Okay, so that sp hybrid orbital is going to basically be our groundwork to make our first bond. Okay, what that's going to mean is that we've got 2 sp hybrid orbitals and then 2 p orbitals. Okay, so these sp hybrid orbitals can establish our connection with the oxygen, and then that will leave behind our 2 other p orbitals, so that sorry, this is sp hybrid orbitals and a p and a p. Our two p orbitals can ultimately be used for what we know as our pi bonds. Okay, so like I was saying, a shortcut for identifying the hybridization is to look at what surrounds that central atom. Another example, if you took up something like NH3, well, NH3 has a total of 3 hydrogen atoms, but it also has a lone pair of electrons. And so we need to take that into consideration. This has 4 things surrounding it. What else did we see that had 4 things surrounding it? CH4. So what is the hybridization of nitrogen? Well, it's going to be sp3. Now what makes this kind of unique is our so-called electron domains, hydrogen, 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 lone pair of electrons. They are different. We have 3 bonding domains and 1 non-bonding domain, so we have a total of 4 electron domains, making our molecule sp3 hybridized. So the last thing that I wanted to talk about from module 4.1 was polarity. Polarity is a measure of how much an individual atom within a bond wants an electron. So if we look at something like CCl4, okay, let's draw that molecule. We've got carbon, 1, 2, 3, 4 Cls. Now, very important and very famous scientist Linus Pauling came up with the Pauling scale of electronegativity. And what he looked at was how much does, well, every single electron, or every single atom within, or I'm sorry, every single element on the periodic table, how much does every element on the periodic table want electrons within a bond? And he assigned values to all of these different substances, and those values for chlorine, for instance, has a value of 3.0. We use a scale that ranges from effectively 1 to 4. The most electronegative element is fluorine, and so basically everything on the periodic table, the closer that you get to fluorine, the more electronegative you are. Carbon, on the other hand, is 2.5. So when we look at this bond right here, chlorine versus carbon, so this bond right here, and we're just going to single out one of them. If we were to talk about where the attraction for those electrons are, well, it's going to be closer to chlorine. So those electrons within this bond are going to be more concentrated toward that Cl. And so as a result, what we do is we come up with a sign for denoting this. And this arrow that I drew basically shows that polarity difference. Okay. Now we can do that for each and every single one of these. We have that exact same arrow pointing towards our more electronegative region, and this one's at a little bit of an angle, arrow pointing, and then basically this positive to show the more electropositive end of that. Now this is an interesting look at every single bond. However, what this does not address is the molecule polarity. Now, molecular polarity, what you're looking at is what is this molecule in terms of its overall polarity? Is this molecule polar? Okay, so when you talk about if a molecule versus a individual bond is polar, well, let's look back at our CCl4. Each one of these carbon chloride bonds is a polar bond. But CCl4 is a non-polar molecule. And a good question is, what gives? Why? The reason for that is each one of these bonds, they have equal strength, and they're equally far away from one another. So what that means is they basically all cancel one another out. Now, if we compare that to something like CCl3F, okay, now we've got 3 bonds, carbon chloride bonds, and we've got a fluoride bond. Okay, fluoride has an electronegativity of 4, 3.0, 3.0, 3.0. Okay, carbon is still 2.5. Okay, so each one of these bonds is polar, but one of them is more polar. That carbon fluoride bond is the most polar bond. Now, what we can do then is we can go ahead and draw our little arrows to denote our direction. But then what we can also do is we can draw an overall direction for this whole molecule. So considering all of, so this, sorry, let me clarify, polar bonds and a polar molecule. So this overall polar molecule, well, what is the most electronegative region of it? Well, the most electronegative region is that F. So we have an overall molecule dipole that is pointed towards our fluorine. Okay, so this is kind of a way to think about, well, you can have a polar bond, and you can have multiple polar bonds, and have a molecule that is overall nonpolar. You have to consider, well, if the molecule is polar, well, why is that? Well, you've got some disparity in the electronegativity and basically the pull of electrons in a particular molecule. So you can have polar bonds, and those polar bonds can cancel one another out, resulting in a nonpolar molecule like CCl4. Those bonds don't cancel one another out, like in CCl3F, then you've got an example of a polar molecule. All right, well, I hope this was helpful, and have a good one.